Welcome to our second lesson on quantitative aspects of chemical change. We'll be looking at concentration calculations today. Now, when referring to the concentration, we're basically referring to the amount of dissolved substance, and the unit for that is usually mole per cubic decimeter. Now, it's very important that you note, though, that when we are going to be making use of concentration and volume is included, that the volume must be measured in cubic decimeters in order to go and calculate the concentration thereof. Now, when referring to the amount of dissolved substance, it basically means any amount of solid particles that has been dissolved inside a solution. That usually means a liquid. Now, for concentration, we're going to have a specific symbol, and this is going to be a small letter C. And as I said, the unit in which we're going to be measuring it is mole per cubic decimeter. Now, the specific formula that we will be making use of in order to go and calculate concentration is made up of moles and volume too. Now, once again, our moles is measured in mole. Volume must now be measured in Volume must now be measured in cubic decimeters, and concentration will then be moles divided by cubic decimeters. One of the most important things just to remember is that everything else is small letters except for your volume, which is capital letters, and that volume must be measured in cubic decimeters. Now, we're also going to be looking at a standard solution. Now, solutions like that is usually solutions of which the concentrations is known and that will stay that constant concentration for a period of time. Now, to make up standard solutions, we're going to be using volumetric flasks. Now, all that's very unique about these flasks is that they're very, very precise. They're far more precise than any of our measuring beakers or our measuring cylinders. And they've got a very thin line here at the top of the neck of the flask, which is going to indicate if you fill it up to there, it will have a specific volume. So every flask is made to be a specific volume. So for example, this might have been 250 cubic centimeters. That means if we start filling it up with our solution, which could be water, and we let it fill right up till that brim of that line, then it is exactly 250 cubic centimeters. So making standard solutions is a very precise type of calculation. That means very exact. Now let's go and apply this to an example. We need to go and calculate the concentration of a standard solution that was made up using 3 grams of sodium chloride that has been dissolved in a volumetric flask with a volume of 200 cubic centimeters of water. So in order to go and calculate concentration, we'll make use of our formula that says moles divided by volume. Now, I do have the volume, it's 200 cubic decimeters, but I do not have the moles. I have been given the mass though, so that means I can go and make use of mass divided by molar mass in order to calculate moles, which I can then go and punch back into my formula to calculate concentration. Now, the mass was given as 3 grams, but our molar mass is that of the sodium, which is 23, plus chlorine, which is 35,5. Now, note between chlorine and copper, those are the only two of our elements on the periodic table with a molar mass that has a specific decimal place. And this gives me a mole value, note though, not rounded off, of 0,0512 with a few decimal places still after that. So from here on, we can go and calculate the concentration. We'll take this mole value with all of its decimal places, and then we will be dividing with the volume, which was luckily in our case already given in cubic decimeters. And that's going to give me quite a small number though. If your calculator is in scientific notation, it will end up giving you 2,56 if you round off to 2 decimal places, times 10 to the power of -4 moles per cubic decimeters. Otherwise, if your calculator is not in scientific notation, it will give you a number of 0,000256, which you can then write down in moles per cubic decimeter. So you just give whatever your calculator ends up giving you at the end as a final answer. Now we're going to also be looking at how we go about diluting solutions. Now let's go and make use of the following as an example. we're going to dilute our solution here that has only 5 particles in it. Now usually when you dilute a solution, you're going to be adding water to the solution. So should we go and add water to the solution and let's say dilute it up till here at the top, then it means our 5 particles will now be further spread apart from each other. Now what's important to note here is that our number of particles in each case, and that number of particles is basically indicated by our number of moles, is staying the same whether it is in its concentrated form here initially or in its diluted form. So that means we can, from using our concentration calculation, which says that moles is equal to concentration times volume, go around and calculating our new concentration when we are using the same number of particles. Now we're going to give them specific numbers so that we can see which one of them was the concentrated form and which one the diluted one. Noting that our N1 and our N2 is going to be equal, it means that we can go and say, but that means C1 V1 will be equal to C2 V2. And this is then our new formula that we'll be making use of when we have a diluted solution to go and calculate either the new concentration or the new volume. Let's go and apply this to an example. So our example starts off by telling us we've got 50 cubic decimeters of magnesium chloride solution, which is a concentration of 2 mole per cubic decimeter. It's then been diluted to a volume of 125 cubic decimeters. What would be its new concentration? Now let's first start off by writing down what do we have. We've got our first initial conditions concentration to be 2 mole per cubic decimeter. We also know that our initial volume which was used was 50 cubic decimeters. Then we went and diluted it and found up to a volume of 125 cubic decimeters what its new concentration would now be. So we'll be using our formula. Now this formula is though not given to you on the formula sheet and you'll need to memorize this one off by heart. So we're going to take the 2 times our 50 cubic decimeters for our volume. C2 is the one we want to go and calculate and the new volume was 125. This gives me a second concentration of 0.8 moles per cubic decimeter. Now the question which I would like you to go and attempt is to go and calculate the concentration of each of the ions used in the solution of 40 grams of sodium carbonate in a volume of 500 cubic centimeters. Now remember to go and first write down what has been given to you, what you exactly want to go and calculate, and from that see which formulas you'll actually need to end up using. Now we need to go and calculate concentration. We'll sort out the concentration of the ions a bit later. Let's just first get to our concentration value. Now in order to get to our concentration value, we'll need the moles divided by the volume. Now our volume was given to us, we'll just need to convert it to cubic decimeters, but our mole value we would still need to go and find. Now we can go and make use of that during our mass divided by molar mass calculation. Now when calculating our molar mass, we've got 2 sodiums, that means 23 basically times by 2, and then we're going to add to that still the carbon plus 3 of my oxygens, which is 16 each, and that's going to end up giving me 40 divided by 106, and now not rounded off though. And now not rounded off though is 0.3773 moles. So we're going to keep our decimal places when we go over to our next calculation, and that's to go and calculate the concentration. So therefore we're going to have our 0.37, all its decimal places, divided by the volume of 500 cubic centimeters. But we need to convert it to cubic decimeters, so we'll be dividing with 1,000 in this case. Now we're going to be rounding off this value as 0.75 mole per cubic decimeter. Now the question further on went actually to ask what is the concentration of the specific ions involved in this compound. Now we have sodium carbonate. Let's see, what does sodium carbonate consist of? It consists of sodium ions, and in this case there's 2 sodium ions and a carbonate ion. Now remember, carbonate is CO3 minus, so we're going to be keeping this ion as a whole. We're not going to break it up into our carbon and oxygen atoms. So if I've got only one of my carbonate ions, then it means I'm going to multiply that one with the 0.75 to give me the concentrations of the carbonate ion. So that means we're going to have concentration of my carbonate ions to be 0.75 mole per cubic decimeters. When we're going to be looking at our sodium though, there's two of them. Now because there's two of them, we're going to multiply our 0.75 by 2. And that's going to give me 1.5 mole per cubic decimeters. And that's then my concentration for my sodium ions. So most important thing is, if there is more than one of them involved, you'll need to multiply that specific number with the concentration value that you've calculated. Now in our next lessons, we're going to be looking at titration and precipitation reactions.